Llevo physics. Anaweza lenda le akanga ya tene na lewa. Ile sindiro ile pele. Okay, pero.
By showing me a thumbs up, just let me know if you can hear me. Hi guys, by showing me a thumbs up, can you just let me know if you can hear me? Okay, thank you. Okay guys, let me just remove this at the bottom here. Right, now let's get into it. If you have a question, I want to check, nothing in the chats yet. If you have a question, please ask. Aluluto, you have a question? Okay. Okay, I think we can start now. I'm recording this meeting just so you guys know. Okay, if you have questions, please ask me. Otherwise, I'm going to start. If you have any pertinent questions, let's just get on with it. Otherwise, I'm gonna start. So I'm gonna wait just for a minute. If you have any questions, you can go ahead and ask me. We are dealing today with both chapter 23 and 24, electric fields and Gauss's law. Okay, both electric fields and Gauss's law. I'm just still making sure, yes, the sound is still there. It is also playing on YouTube, so that is good. Let's go to our first question. Okay, since there are no questions, I will be periodically checking the YouTube, or rather the Teams meeting, for any questions, and YouTube if there are any questions. Otherwise, I will be continuing slowly. First question. During a physics lab, okay, this is a physics practical, so during a physics practical, just raise it up so you can see the question better. During a physics lab, that just means during a physics practical, a plastic strip was rubbed with cotton and became positively charged. Okay, so we have a plastic strip We rubbed it with cotton and it got positively charged. The correct explanation for why the plastic strip becomes positively charged is, so let's draw that situation. Let's say this is a cotton rubbed with cotton. So let's say this is a piece of cotton. This is cotton. And we have a plastic strip. It's a piece of plastic. Okay. We rubbed it with the cotton and it became positively charged. Now, what do we know about charges? Okay, the only charges that move are electrons, so only electrons move. So in this case, when the cotton rubbed against the plastic strip, the electrons moved out of the plastic strip and into the cotton. Okay, so the electrons move out of the plastic strip and into the cotton. This is what has happened. Do you guys agree? By show of hands, a thumbs up if you agree with me. This is what happened. Thank you for you guys that are participating. Thanks. Okay, that is indeed what happened. Let's go look at the options for an answer. Okay, select 1. The plastic strip acquired extra protons. That is wrong. The plastic strip, protons do not move. Okay, you need a tremendous amount of force to move protons. In fact, it's one of the strongest. It's called the strong nuclear force. You need to overcome that. B. The plastic strip acquired extra protons. No, there was no movement of protons. C. Protons were created. We cannot create any masses out of nothing. The plastic strip lost electrons to the cotton during the charging process. D. D is the one closest to what we described. And the correct answer is yes, it is D. Okay, so the answer is D. It's the correct answer. Question 2. This is just the baby questions. Okay, it tests your conceptual understanding of what is happening during charging. Okay, if you cannot answer these questions, you won't be able to answer the more involved questions. Because this stage tests your understanding. Question number 2. A student rubbed a glass object and a felt cloth together. Okay, and the glass becomes positively charged. Which of the following statements is or are true? Okay, so there can be multiple statements that can be true. Okay, so we have exactly the same situation. Let's say we have a glass rod. Okay, the student rubs it with a piece of felt. This is felt. Felt cloth. They rub this this piece of glass, and the piece of glass becomes positive. So the exact same thing happens as before with the plastic strip. The piece of glass becomes positive. Now we need to circle all that apply. Okay, so all that applies. Number 1, the glass gained protons during the rubbing process. That is wrong. Okay, number A, let's say A, wrong. B, the felt became charged negatively during this rubbing process. B is correct. The felt gained electrons during the charging process. C, charge is created during the rubbing process. Is charge created? No, that is wrong. D, if the glass acquired a charge of positive 5 units, then the felt acquires a charge of negative 5 units. Okay, that is true. The charge will always be equal. If you add them up, they must equal the original net charge. So D is true, and then we have an E, I believe. E. Once charged in this manner, the glass object and the felt cloth should attract each other. Yes, the glass is positively charged, the felt is negatively charged, so they will attract each other. There will be a force of attraction. So the correct answers are B, D, and E. Okay, let's check. B, let's choose B, we choose D, and we choose E. So B, D, and E is correct. Let's check. That is correct. The correct answers 1, 2, and 3. B, D, and E are the correct answers. Okay. Question number 3. I have found that students tend to struggle with simple type of problems like this. And these are the problems that make up your multiple choice most of the time. Okay, let me see. No questions yet. None. No questions. Okay. Question number 3. Metal sphere A. This is metal sphere A. This is metal sphere B. Metal sphere A has 4 units of negative charge. So 1, 2, 3, 4. And metal sphere B has 2 positive units of charge. So 1, 2. The 2 spheres are brought into contact. What is the final charge? So we bring them together, they touch. Remember, they are metal. So they touch. There is a net flow of charge. We move them, we separate them from each other. What is the charge on each of these spheres? Okay, what is the charge on each of these spheres? And explain why. Okay, there is a simple law in order to do this. Okay, one, it's just simple arithmetic. So we have here negative 4, and here we have plus 2, positive 2. Okay, we bring them together. So basically we have negative 4 plus 2. We brought them together. But what happens to charge? In this case, they are both metal spheres. The charge will be distributing equally amongst all the participants. In this case, there are 2 spheres, so the charge will be distributed equally amongst these 2 spheres. Therefore, it will be negative 4 plus 2, that's negative 2 divided by 2, which gives you each one of these spheres will have just one negative charge. Okay, one negative charge. So each of these spheres will have one negative unit of charge. Okay, because charges, when you add them together, you can add them arithmetically, and then they will distribute equally amongst these spheres. A lot of people would have said the net charge is just negative 2. The net charge for the whole system would be negative 2, but for each individual would be negative 1. Now let's check and see whether we are correct. That's the wonderful thing about doing problems like this. We can also check and see if we are correct. Negative 1. The answer is negative 1. What is the reason? Because negative 4 plus 2 is equal to negative 2. And the remaining 2 charges distribute on both spheres so that each sphere will have a negative 1 unit. That's it. It's negative 1, can't be this one which says negative 2, can't be negative 3, can't be negative 4. Let's check our answer of -1. The correct answer is -1 because of the reason that we just provided. Question number 4. Two neutral conducting spheres. Okay, so they are neutral.
Sorry, sir, you are muted.
Okay, let me see.
We can't hear you.
My apologies. For some reason, this thing mutes me automatically. I need to actually set this. Okay, can you guys hear me now? Okay, thank you. Did you guys follow the last problem? Why there? Thank you guys. I just had to put down the noise suppression. For some reason it turns noise suppression on automatically on Teams, and it considers me speaking as noise after a while. I don't disagree, but it's kind of hurtful. Okay, so let's check. Did you guys follow the last problem I did, problem number 3, as to why when you bring two metal spheres or two conducting spheres into contact with each other, okay, the charge is distributed evenly.
Oh, so I didn't hear you. You're muted.
Okay. Okay, quick explanation. Or rather, an explanation. Let me just watch that. When you have two spheres, one has a charge of, it's -4, I believe. Let me just check. One has a charge of -4 units. That one just looks like a terrible grin on that thing. Two metal spheres, one has a charge of -4, one has a charge of +2. The question is, if we take these two spheres, make them touch each other, okay, bring them into contact, and then separate them again, what would be the charge on each one of these spheres? Okay, it is simple. When you bring them together, let's just write that this one has a charge of -4, this one has a charge of +2. Okay, now when you bring spheres like this, conducting spheres together, you can just simply add the charges. Okay, you can add the charges. It's -4 plus +2. Okay, I don't write the plus, but let me just rather do that. Plus +2. Okay, now when you add charges like this, whatever charge is left over is distributed equally amongst the participants. Okay, in this case there are two spheres, so we divide it by 2, and what we're left with is -4 plus 2 is -2 divided by 2. Therefore the charge on a single sphere would then be -1. Does that make sense? By show of hands, does that make sense to you? You add all of the charges together, and whatever is left over, the net charge is divided by how many participants there are. Okay, so if there were 3 spheres here, let's say we add a third sphere with a -2 charge, a -3 charge, with another -4 charge. Let's add another -4. This whole problem would then become, we just add the 4 charge plus -4, and This would then become negative, negative plus, that's negative 6. So the answer would be, we need to divide how many? Not by 2 anymore, we need to divide by, let me just rather do this whole problem again, doing these 3 charges. Doing 3 charges, okay? Let's say, if I was to add another charge, and this one is also negative 4, okay? And we bring them all in contact, and then we separate them again. We have that in order to calculate the charge on a single sphere, we would say negative 4 plus positive 2 plus negative 4, and we divide by how many participants there are. In this case, there are 3 spheres. Okay, so it's negative 4 plus negative 4, that's negative 8, plus 2, that's negative 6, divided by 3. So the answer is negative 2. Each one of these spheres will then have a charge of negative 2 if you bring them in contact and then separate them again. That is a simple concept. Okay, question number 4. Let's look at what question number 4 wants us to do. Okay, and yes, these questions does seem very easy to some of you, but we usually, or these questions are usually put into tests and exams as multiple choice, and I know usually the multiple choice gets to 20 marks out of 150, and it's mostly this type of questions, and then the students always get it wrong, okay, most of the time. That is why we put them into the tutorial, so that you understand how to do or how to approach a problem like this if you ever encounter one. Okay, so we have 2 neutral spheres. Okay, question 4, we have 2 neutral conducting spheres. Okay, so we have 2 spheres, they are both conducting, and they have a no net charge, a zero charge, a zero net charge. Okay, they are conducting, yes, but they are also neutral, meaning the amount of positive and negative inside of each one of them is exactly equal. So they are neutral. A positively charged rod is brought near the right sphere. Okay, let me just put it here. Let's say each one of them, they are neutral, so each one will have a positive and a negative. Doesn't matter how many, but for each positive there will be a negative. Okay, let's say both of these are conductive, but they are also neutral, because if you add up the positive to the negative, it's zero charge. That means it's neutral for both of them. But now they say we bring a positively charged rod near. So this is the rod, it's positively charged, and we bring it near the right sphere. Okay, the positive, remember, or please note, we are bringing it near, we are not making them touch, we are just bringing it near. Okay, there is still a gap between them, near the right sphere. What is going to happen if we bring this sphere near this thing? All that's going to happen is all the negative charges are going to be attracted to that side of the sphere. That's it. Okay, the positive rod is then removed. The result is, what is going to be the result? Okay, this positive rod is just going to attract the negative spheres towards this side of the sphere, the right side of the sphere, and when you remove it, the charges are going to distribute equally again. So you're going to end up with the exact same situation that you started with. Okay, so all this positive rod did was just move the negative charges towards the right, and when we removed the rod, the positive rod, the charges move back to their original places. Okay, so the result is the left sphere is negative and the right sphere is positive. That's not correct. The left sphere is positive and the right sphere is negative. That's not correct. The left sphere is neutral and the right sphere is negative. Not correct. D. The left sphere is negative and the right sphere is neutral. The answer is E. Both spheres are neutral. Okay, it is exactly the same situation. Both spheres are neutral force. Answer is D. The answer is D. Okay. By show of hands, who understood why the answer is D? Because there was no net movement of charge. Okay. The charge moved on the spheres themselves, yes, but they did not move out of the spheres. Okay, thank you. Now let's continue. Question 5. There is about 8 of these easy type questions, and then the rest are Gauss's law. Okay, I believe you started with Gauss's law. Okay, and flux. So here we have question number 5. Object A has a charge of 2 nanocoulomb plus 2 nanocoulomb. So we have object A. It is 2 nanocoulomb. And then we have object B, 6 nanocoulomb. Okay. Which statement is true about the electric forces between these two? Okay. The force, this is A, and this is B. What do we know about the forces between these two? Is the force of A, B, the force that A has on B, is it equal to negative? Okay, instead of reading that and confusing you, what does Newton's third law state? Okay, if this one exerts a force on that, if A exerts a force on B, B will exert a force on A, but the only difference is the direction of the force that B will exert on A. So the force, without looking at whatever options they give us, the force that A has on B will be equal to the force that B has on A. Does that make sense according to Newton's law? Let me just stop there. Does that make sense? This is Newton's law. It doesn't matter what the charges are. Thank you, Hank. And Camogelo. I apologize if I did mispronounce your name. And also only a student number there. Okay, so you all agree this is Newton's law. Doesn't matter what the charges are. This law will hold. Force that A exerts on B will be the same as the force that B exerts on A. The only difference is the direction. Okay. B will exert a force in the opposite direction. That's it. So the force that A exerts on B will be negative the force that B exerts on A. You can write the negative on this side or on that side. It doesn't make sense. It doesn't matter. It's the same mathematically. So let's check. There it is. The force that A exerts on B is equal to the force that B exerts on A, but in the opposite direction. In this case, the negative just denotes the direction. Okay. Question 6. These questions, or these type of questions, are the bread and butter of multiple choice. Okay, I remember one year Prof. Olivier put 40 marks out of 150 was just multiple choice. Okay. Each multiple choice question counted 2 marks, and there were 20 multiple choice questions. Most of them like this. It was a free for all for everyone. And still people managed to guess the wrong one. Okay. We have 2 small non-conducting spheres. Okay, this means the charges are not free to move inside of these spheres. So each of 2 small non-conducting spheres is charged positively. Okay, so this is a positive charge, it has a positive charge. Okay, when the 2 spheres are 50 centimeters apart, 50 centimeters, that's half a meter. So when they are half a meter apart, each sphere is repelled from the other by a force of 2 newtons. Okay, I can see where this is going. determine the magnitude of the smaller of the two charges, okay? So here we have a very, very interesting problem, okay? We have two spheres, they are positively charged, both of them, and the force between them when they are half a meter apart is 2 newtons. We need to solve for Q1 and Q2, okay? Let's continue. So we know the force between two charged particles is equal to K Q1 times Q2 over R squared. That is the force between two charges, okay? Now we know that the force between them is 2. I'm not going to write in the units, okay? I'm just writing the numeric values. K is 9 times 10, or this is Coulomb's constant, 9 times 10 to the 9. Then we have Q1 times Q2 over 0.5. When we're doing this type of problems, please convert everything to SI units. If you use this in centimeters, it will work, but then you have to convert Coulomb's constant to SI units as well. What you're left with is 2 times 0.25, and what you're left with on this side is 9 times 10 to the 9, 0.25. And on this side we have Q1 times Q2, okay? Simple algebra, okay? Therefore, if we Q1 times Q2 is equal to 5,562 times 10 to the negative 11. Okay. If you want to know the units, it will be charge squared because you are multiplying two charges, so it will be Coulomb squared. Okay. So all we did right now was we just found one equation, okay, one equation, okay, but we need to solve for two variables, okay. We have Q1 and Q2, two unknown variables, okay. So we need to solve for two unknown variables. Okay, this is number 6. Sorry, I said number 7. This is number 6. So we have equation number 1. But what have we also been told? Okay, or we should read from the question. They tell us the combined charge being 40 microcoulomb. Okay, 40 microcoulomb. So we also have that Q1. Let's first write what we originally had. Q1 times Q2 is equal to 5,56. We just determined it. We just determined this. And then our second equation, we know that Q1 plus Q2 should be equal to 40 microcoulomb. Okay, now micro is 10 to the negative 6 coulomb. That is Coulomb squared. Okay, so here we have two equations. You don't just have to solve each one of these equations. Okay, if you solve for Q2, let's just make Q2 the subject of this formula here. Q2 therefore is equal to 40 microcoulomb. 40 times 10 to the negative 6 minus Q1. You can of course have chosen to solve for Q1. I just did it for Q2. Why? Doesn't really matter. Okay, so here we have two equations. Equation number 1 and here we have equation number 2. Okay, now we can substitute equation number 2 into equation number 1, and if we do that, if we substitute equation number 2 into equation number 1, we have that Q1 is still there from first equation, but now Q2 is equal to 40 times 10 to the negative 6 minus Q1 equal to 5,562 times 10 to the negative 11. Okay, so there we have it. We just now have to solve or make a quadratic equation. Okay, and if you go about it carefully, you'll find that it's Q1 squared minus 40 times 10 to the negative 6 Q1 plus, that's times Q1, plus 5.562 times 10 to the negative 11 is equal to 0. So there we have a quadratic equation. Okay, you can try to solve it the normal way, but the easiest is just to use the quadratic formula. Okay, if you use the quadratic formula, Q1 is equal to, and I don't need to write this out, but I will, equal to B 40 times 10 to the negative 6 plus minus the square root of B squared. This is negative 40, by the way, so it should actually be the negative B, so that's negative of negative, so I just wrote it as a positive immediately. This is B squared, so it's negative 40 microcoulomb 10 to the negative 6 squared minus 4AC. Okay, I can't fit them in there, over 2A. Okay, so 2A, so 2, 1. A is 1 and C is 5.562. Okay, I just fit in B here. Remember, this is A, this is B, and this is C. Okay, in the standard quadratic equation. Okay, so one value is equal to Q1 is equal to 38,56 times 10 to the negative 6 microcoulomb. Okay, that's Q1. Okay, and in order to get Q2, you just subtract this value. It's just 40 microcoulomb minus 38.5 microcoulomb. Okay, and there you have your answer for both Q1 and Q2. Question number 7. That was an interesting question, and you will see something like it's similar. So just make sure you understand how that question is done. Okay, it is just basic quadratic simultaneous equations. Okay. Question number 7. Here is 7 actually. The diagrams below show two uniformly charged spheres. Okay, so both of these charged spheres are uniformly charged. The charge on the right sphere is 3 times as large as the charge on the left sphere. Which force diagram best represents the magnitudes and direction of the electric forces on these two spheres? Okay, remember we just did a problem just like this, but in that problem we determined f of a b is equal to the negative of f of ba. Okay, therefore if we take that as, and we saw that it was correct, okay, that means in these two spheres, okay, the force or the length of these arrows must be exactly the same, but the arrows will be pointing in opposite directions. And the only one that satisfies that criteria, where the arrows are the same size and they are pointing in the opposite direction, is number 4. Okay, so the answer is number 4. Okay, and let's check. There it is. Number 4 is the answer. It's exactly the same problem as we did earlier. It's only this time they give us a drawing instead of working with the symbols. Okay, question number 8. Then we're done with this type of problems and we go into Gauss's law. So question number 8. A very interesting question. It says a negatively charged particle with a charge of 1 microcoulomb is placed at the center of a uniformly charged cube. Okay, so we have a cube. So we have a cube. Forgive my terrible drawing. Okay, that looks more or less like a cube, and in the center of that cube is a negatively charged particle, a negatively charged particle. Each of those cube has a side of 1 millimeter, meaning each of these faces has the exact same. Each of those faces has the exact same area, and a total charge of 3 microcoulomb is spread out over all 6 faces of the cube. What is the total force acting on the particle in the center? Find the magnitude and the direction. What's the total force acting on the particle in the center? The answer, it might surprise you, is, from you guys that are still listening, what would you guess is the answer? Okay, what would be the force? They ask there, is it the force or the charge? Find the magnitude and direction of the total force. Okay, the total force. Those of you who are still listening, can you type in the questions? What do you think is going to be the answer? Or you can just unmute yourself and then tell me what you think the answer will be. Anyone want to hazard a guess? What do you think is the force, the net force on that particle directly in the center of this cube? If there are charges all over the faces of this cube, yes, I see 2 answers already correct.
0, sir.
Yes, someone told me as well. All of those of you who have answered the correct answer, yes, is 0 newtons. Reason being, a cube is symmetrical, right? And this thing is directly in the center, okay? Which means for every piece of charge on the top surface, there's an identical piece of charge at the bottom surface, okay? Okay, which means those 2 charges will attract it or push it in opposite directions. So every single charge will have a direct symmetrical opposite, which will cancel it out. That is why the net charge on this thing will be 0. Okay, the net force will be 0. It will have forces, yes, from every single direction it will have forces, but the net force will be 0, because every single force will have an opposite but equal force on this cube. Thank you very much, those of you who gave the correct answer, and those of you who were afraid of answering and you also figured out the correct answer. Thank you. Okay, now we go to the meat of the problems. Okay, we won't be long. It's just 5 problems. Problem number 25, from 25 onwards. Okay, this has to do with electric flux. Now for PHYV, I think Dr. Ugesa is having a tutorial on Friday, and this will be helping you. That's why we are having such a comprehensive session. Okay, so question number 25, the total electric flux. By the way, before I begin, let me just refresh your memories. Electric flux, just get here in my notes, find myself. The electric flux passing through a surface, the electric flux. The reason why we actually denoted electric flux is later on you're going to do magnetic flux as well. Electric flux through a surface, okay, is equal to the enclosed charge. That is the charge enclosed, okay, whatever is enclosed by the surface, divided by E naught, okay, divided by E naught. Later on you'll deal with mu naught. Okay, this is the permittivity of free space. Mu naught is the permeability of free space. You will deal with that later. So what this is Gauss's law. Okay, this is Gauss's law. This is the essence of Gauss's law. The total electric flux passing through a closed surface. Okay, later on they will tell you that the surface is a sphere most of the time. Okay, but this is the essence of Gauss's law. This is what you need to solve all of these problems. Okay, so if they ask you anything about electric flux, your first question or your first equation should be this one. Doesn't matter. Later on you're going to deal with a nice equation where you just 4 pi r squared the whole time. Just remember, Gauss's law in essence simply states that the electric flux through any surface is equal to the amount of charge enclosed divided by the permittivity of free space. So it's only dependent on if there is charge enclosed. Okay, so the problem says the total electric flux through a closed cylindrical length. It has a 1.2 meters of length, a diameter of 0.2 meters. The surface is equal to -5 Newton meters squared per coulomb. So that's the electric flux. Determine the net charge within that cylinder. Okay, so they tell us we have some sort of a cylindrical surface. Okay, there's the cylinder. They were even kind enough to give us, there's the charge inside, wherever it's inside. They gave us that the diameter is 0.2 meters. We have a diameter of 0.2 meters and a length of 1.2 meters. Okay, so there's the cylinder with the enclosed charge. They want to determine what is the net charge in within. Okay, we can assume it's somewhere in the center. You don't have to, but it has to be inside the cylinder. Okay, so what is this net charge inside the cylinder? We know from Gauss's law that the net flux, the net electric flux, is equal to the charge enclosed, Q enclosed, divided by the permittivity of free space. Okay, but we have Q enclosed, we have the electric flux. It is -5 Newton meters squared. Okay, so the charge enclosed, therefore, the charge enclosed is equal to the electric flux multiplied by the permittivity of free space. That is how you get the charge enclosed. So charge enclosed is equal to, what is the flux? It's 5, negative 5. Negative 5 Newton meter squared per coulomb. That is the flux multiplied by the permittivity of free space. It is a constant. It's 8,85 times 10 to the negative 12. I'm not going to write its units, I don't have space. If you multiply those two together, you have that the enclosed charge is negative 4,4 times 10 to the negative 11. So it's negative 4,4 times 10 to the 11. But if we move this decimal point to the right, that becomes negative 12. So it's this is coulombs, so it will be picocoulombs if we move the decimal point. So it will be 44. So the answer therefore is negative 44 times 10 to the negative 12 and any coulomb. So we can just write it as negative 44 picocoulombs. Okay. By a show of hands, who understood that problem? Those of you who are still paying attention, who understood the problem? It was a simple problem, we just had to find. Thank you guys. Now, the next one. (26). Question number 26. Still Gauss's law. Okay, so they tell us, don't worry about the numbers for these problems. These is just for our record keeping. It is just so that we can keep track of who's doing which problems with the students, so we don't accidentally do each other's problems. Okay, so we have a situation. Charges Q and Q, small q and big Q are placed on the x-axis at x equals 0 and x equals 2 meters. Okay, so here is the whatever's happening. So small q is placed on the x-axis at x equals 0. So here's x equals 0. So small q is here. Let me just write in a different color. Small q is right here, placed at x equals 0, and big Q is placed at x equals to 2 meters here. Okay. So this is x equals 0, and this is x equals 2 meters. Now they tell us if small q has a charge of negative 40 picocoulombs and big Q is plus 30 picocoulombs, determine the net flux through a spherical surface of radius 1 meter. So the radius, so that's 0 meters, that's 2 meters, so 1 meter is somewhere here, 1 meters, there's 1 meter. So the radius of a sphere of 1 meter, there's that sphere of 1 meter. What is the net flux through that sphere? Okay, so what we do then is we take the formula for Gauss's law, which says the electric flux is equal to the charge enclosed over the permittivity of free space. In this case, what is the charge enclosed? How much charge is enclosed? Okay, how much charge is enclosed? Negative 40 only. Only the small charge is enclosed. The big charge falls outside of the sphere. Okay, so only the small charge is enclosed. Small q is enclosed by this sphere because we want the flux through this sphere of radius 1 meter. So if we actually do the problem, the electric field, the electric flux through the surface is equal to the enclosed charge divided by mu naught. The enclosed charge is small sphere, it's 40 times 10 pico, so it's 12 coulomb, divided by the permittivity of free space is 8,85 times 10 to the 12. So basically 40 divided by 8, negative 4,5 newtons meter squared per coulomb. Negative 4.5. Okay. If you understood that question, just give me a thumbs up. Okay, you understood that only the small one was inside the sphere. Thank you very much. Okay, the last one. Okay, I think there's a few more. Okay, about 27. We're going to 29. So let's say this is question number 27. You don't need to care about the actual lettering or the numbering like I said before. A point charge, positive Q, is located on the x-axis at x is equal to A. Okay. So let's draw it again. So here we have the x-axis. So where x is equal to A. So let's call this where it is A. They don't tell us the numerical value of A. They just say where x is equal to A. And a second point charge, this is where positive Q is. Let's put it in there. This is where positive Q is. Positive Q is at A. This is where positive Q is. Now let's find out the other one, or the rest of the information. A second point charge, negative Q, is located on the x-axis at x equal to negative A. So negative A will be about the same distance away. That's negative A. And there you will find a charge, and that charge is called negative Q. Okay, so at those 2 points we have these two charges, positive and negative. Now a Gaussian surface, okay, with a radius 2a. So we are going to draw a sphere, and this sphere has a radius of 2a. Okay, this is A. 2a should be here. Let me just rather draw this. So this is A. So 2a should be here. And then A, so negative 2a should be there. So they tell us a Gaussian surface with a radius of 2a. Okay, so this Gaussian surface is centered at the origin. So the origin, from the origin to 2a, that would be our Gaussian surface. The flux through this Gaussian surface is, we need to determine the flux. Let's first find the sphere. So it is centered at the origin, but it goes through 2a. So it will go there, 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 something like this. It will touch there at 2a and also there at negative 2a. Okay, so there's your surface. Okay, now they ask us the flux through this Gaussian surface is. Can any one of you hazard a guess in the comments, or either just unmuting yourself? What do you think is going to be the net electric flux? What do you think is going to be the net electric flux through the surface? You can type it. What is the net electric flux through the surface? Remember, the blue is the surface. Let me see if the blue actually shows up. Yeah, it does. Anyone? Yes. Yes. Correct. Yes. Kamogelo.
Can I
Ntutuko.
ask, sir,
Yes. Go ahead.
why is it 0?
Why is it 0?
Yes, sir.
Remember, what does the formula say? It's the net enclosed charge. Okay. What is the net enclosed charge here? So it'll be the net charge inside the surface will be positive Q plus negative plus positive
Oh,
Q. This will give you a net
0.
charge of 0.
I see. Thank you.
Okay, cool. So the net charge inside the sphere, the enclosed charge is 0. The charge enclosed is 0. We divided by the permittivity of free space, so the answer is 0. Okay, the answer is 0 because the flux, the net enclosed charge is 0. When they ask about enclosed, we add all the charges inside that surface of sphere or that block or whatever. All the charges inside that sphere, if we add them all together, that net charge is the one we divide by the permittivity of free space to get the flux. In this case, if we add positive Q to negative Q, we get just 0Q, and that is why our answer should be 0. 0 because the negative flux over one hemisphere is equal to the positive flux. You can also say that. Okay. The reason what they mean here, 0 because the negative flux over one hemisphere. Let me just explain that quickly. Okay, the simplest answer is the enclosed charge is 0, but this is a charge, right? This is a negative charge, which means the charge will flow towards the negative, and it will go away from the positive, exactly symmetrical. But what is flux? It's the amount of lines going through the surface per unit area. So if you add up all the positive flux on this side and you add them to the negative flux on the right hand side, they will be exactly equal, which means one will be positive flux and the other will be negative flux. So the total flux will be 0. Okay, that is why they explained it like that. Okay, I also did the wrong. I said 29 again. It was supposed to be 27, I think. This question was 27, not 29. We are ending at 29, so this is our second to last question, and this is a problem that I want you to think about. For closed surfaces, this is question number 28. We have 4 closed surfaces, okay? S1, S2, S3, S4, okay? And there are charges negative 2Q, Q, and negative Q inside these 4 surfaces, okay? The colored lines are the intersections of the surfaces with the page. What is the electric flux to surface 1 to surface 4? Okay, so you first need to calculate the electric flux through for each one of those surfaces. Okay, for surface 1, this is a problem I personally have asked before. So for surface 1, okay, how do we calculate electric flux? We take the entire charge inside that surface. Let's find surface 1. Surface 1 is the brown surface there. Okay, surface 2 is blue, surface 3 is black, and surface 4 is green. Okay, so for surface 1, the flux through there would be, it will always be divided by the permittivity of free space. So what is the enclosed charge in surface 1? Let's just trace out surface 1. Every charge inside the brown surface is, there's a plus Q there. I see plus Q. And I also see a negative 2Q. Negative 2Q. Okay. So if I add this up, it is plus Q, negative Q. So it is negative Q over mu naught. by a thumbs up if you understood why I got negative q over mu naught, or not mu naught, the permittivity of free space, E naught. Give me a thumbs up if you understood why I got negative q. Okay, so some of you understood. You just look what charges are enclosed by that surface. Okay, let's look at surface number 2. S2 is the blue one. What charges are enclosed by S2? There is, I can see inside the blue surface there is a negative q again, and there is also a plus a positive q also, and there is also mu naught. So this is the enclosed charges. So negative q plus q, that is just 0 over mu naught. So 0 over mu naught is nothing but, we can just write 0.
Sorry, sir.
Yellow, go ahead.
So does this mean that the object or the surface is neutral?
Yes, the surface is just some abstract thing that we use to describe. Okay, it's not something that is real. Does it make sense? It's a abstract construct.
Yes, sir. Thank you, sir.
Of course, in a real situation, if we had a surface, it would have its own charge and whatever. Okay? But in this case, it's some abstract construct.
Understood. Thank you, sir.
Okay, S3. Let's see for S3, what inside S3, this is the black surface. Okay, so we have inside that black surface there, we have, ignore everyone else, you just focus on the black surface. So we have there, inside it, we have the negative 2q is inside it, plus we have the positive q, and then we also have plus the negative q over the permittivity of free space, and that gives us negative 2q, negative q plus q, that's negative 2q over mu naught. Negative 2q over mu naught, and then I'm going to do S4 here. And S4 is going to be a simple answer. Look at S4, it's the green one. There are no charges enclosed in it, so it is just going to have a flux of 0. So all the fluxes is negative q over mu naught, 0, negative 2q over E naught, and then 0 again. So it's negative q over E naught, 0, negative 2q over E naught, and 0 again. So A is a potential answer. Let's look at the others. There is also, nope, no, can't be all 0. Nope, yes, A is the only one that's viable. Let's check it. The correct answer is the one we chose. Okay, now for our last problem, question number 29. And I already showed the answer quickly, but you guys will immediately understand why that answer is. Okay, I've already shown the answer, but you will understand why it is that. Okay, so consider a closed triangular box. Listen guys, this problem is I'm going to read the question and I'm going to explain to you in the old days what we did with this problem. Consider a closed triangular box resting within a horizontal electric field of E equal to 7,8 times 10 to the 4 newtons per coulomb as shown in that figure. What is the net electric flux through the entire surface of the box? Okay, through that entire surface of that box, the net electric flux is going to be, you just use Gauss's law, electric flux is equal to enclosed charge over mu naught. How many charges are enclosed there? They didn't say anything about charges enclosed, so we assume there are no charges enclosed, so the electric flux is 0. Here is the problem. Well, not the problem. The answer is 0. Okay, based on the fact that there are no charges enclosed. That's simple. But this is the final question in this problem, because originally this question asked you to first calculate the electric flux through the back surface, then the electric flux through the slanted surface, then the electric flux through the two triangular surfaces, and then when you add up all of those fluxes, you will find that it is zero. Okay, does that make sense? Do you guys understand? First of all, it is zero because there are no charges inside. The flux through it is zero. Okay, so you understand that because there are no enclosed charges. Then the second thing is, if they ever ask you to do this, you can actually calculate the flux through the back surface because you have the area. You can calculate the area of the surface and you have the electric field. Okay? So you can actually calculate the flux. Because I believe it's area multiplied by the electric field. E dotted with area. That will give you the flux. So there are three, let me just describe. So this is how you calculate flux, if I'm not mistaken. And then for the back field, the back part of this triangular box, it is a square. The back side is a square. Okay, you have the measurements. And then you have the slanted area or the triangular part on both sides. And then you have the front slanted area. All of them have lengths that you can calculate. So you can actually calculate the electric flux through each one of these surfaces. And you'll find that the electric flux here would be positive. But for this one, it will be zero for both of them, and the electric flux through this one, it will be negative. And if you add up all of these different fluxes, you will find that it will be zero or very, very close to zero depending on how you round. Does that make sense? By show of thumbs up, if you were to calculate it, that is the answer you would get. You would still get zero, okay, because some of the flux would enter the surface and some would exit the surface, giving them positive and negative. Okay, and that's all that we have time for today, guys. Thank you for those of you who participated. Made things better. Made me feel like I was not speaking to myself. I think either Dr. James will be either later today or tomorrow. There will be Arnold. So, but you will see me next week, Wednesday. I will again send out an email. I will send out a link for a Teams meeting. I need to stop recording as well. And you can join me again if you want. And by the way, if you do, if you have a specific problem that you are struggling with, just email it to me. I will work on it for you and then I can explain it on the next session. Okay? Enjoy the rest of your day, guys. Thank you for listening and enjoy. Some of you have electronics. Thank you.